Hello everyone. In this video, we are going to study about the oscillators as well as the feedback amplifiers. In the previous videos, we have studied about the BJT applications, wherein which we studied about the BJT applications as an amplifier and BJT application as an switch. After that, we came across we came across another few videos which was based on the feedback amplifiers. The feedback amplifier, we studied what is a feedback amplifier and what are all the types of feedback amplifiers. And we also studied the negative feedback amplifiers, and in that negative feedback amplifiers, we also went through a particular kind which we called as voltage series feedback amplifier, and we also saw the negative feedback amplifiers is going to reduce, that is, it is the gain of the negative feedback amplifiers is going to get reduced by a factor of 1 by 1 plus A beta. And after this, we are going to concentrate on oscillators. Before going into the oscillators, let us have a quick look at the quick look of the gain stability of the feedback amplifier which we have studied so far. The textbooks that we refer for this are D.P. Kothari, I.J. Nagarad book titled as Basic Electronics, 2nd edition, and the second textbook that we referred is Thomas L. Floyd, book titled as Electronics Devices, Pearson Education. So we already in the previous video we have told you what is a feedback amplifier and what is a negative feedback amplifier, and we also studied about the voltage series feedback amplifier, and we also saw how the gain was voltage gain with how the voltage gain with the feedback and how it was reducing by a factor of 1 plus A beta. Now let us see the gain stability with feedback. So let us first consider the voltage gain of a negative feedback amplifier, which is given by AF is equal to A by 1 plus beta A, and since A beta is much greater than 1, we can substitute our voltage closed loop voltage gain as equal to AF equal to A by A beta, AF equal to A by A beta, where AF is equal to 1 by beta. So when we look into this relation, it says that the voltage gain of a negative feedback amplifier totally depends on the feedback factor, that is what is feedback factor ratio beta, that is entirely dependent on the feedback amplifier and the feedback factor which is given by the feedback factor beta. Therefore, the gain is not affected by any change in device parameters, that is, even though if we change any of the parameters the gain of the feedback amplifier is not going to change with respect to those parameters, whether it could be in terms of supply voltage or whether it could be in terms of aging of the circuit components. So this will not have any effect on the gain of the gain of the feedback amplifier. Since the feedback network consists of stable elements like resistors, capacitors and inductors, it is not needed to have a it will not change the gain with respect to the change in the parameters. Hence the voltage gain with feedback is more stable. That is, according to the stability, we say it now as a more stable circuit. Suppose if we suppose if there is a certain change in the internal gain of the amplifier is going to take place, we can find the corresponding change, percentage change in the overall gain of the feedback amplifier is given by, we can do this by differentiating the equation with respect to A. So we have the expression as let's we have the expression as AF equal to 1 by or A by 1 plus A into beta. When we differentiate this gain with respect to A, then we get the expression as DAF by DA into is equal to 1 plus A beta into 1 minus A beta by 1 plus A beta squared. A beta whole squared. Then DAF by DA equal to 1 plus 1 by 1 plus A beta whole square. Multiply and divide this, divide RHS by A. So A gets cancelled. We have DAF by DA equal to A by 1 plus A beta into 1 by A into 1 plus A beta. Now once we do this, again differentiate, rearranging the differentiated terms into DAF by DA equal to AF by A into 1 plus A beta. DAF by AF equal to DA by A into 1 by 1 plus A beta. Since we have 1 plus A beta is greater than 1, the percentage change in A is seen to much less than the percentage change in A. That it means that whenever we have the term 1 plus A beta in the denominator, if that factor is greater than 1, the percentage change in the closed loop gain AF is seen to be much less than the percentage change in the gain of the amplifier without feedback. So this is what is the inference, that is stability, which speaks about the stability of the feedback amplifier. So let us have a look at the problem where an amplifier is going to have a gain of 500 without feedback has an overall negative feedback applied which reduces the gain to 100. Calculate the feedback fraction. So the problem gives the data, the following data, that is the amplifier has a gain without feedback. So without feedback is A, that is what we have written. So A, that is what is represented here. A is equal to 500, and one more gain, that is has a negative feedback applied which reduces the gain AF equal to 100. Now let us calculate the feedback fraction, that is we have to find out the feedback fraction. So feedback fraction is AF equal to 1 A by 1 plus A beta. Substitute that and get the answer for. Let us solve this, resolve this, and get the expression for A beta and solve it for beta. So A by AF minus 1 into, transfer this A on this side. So this is going to become 1 by AF minus 1 by A, and substitute the values of AF and A such that we get the beta value as 0.008, or we can also write it as 0.8%. So this is what is the feedback fraction that is required to get a gain, open loop gain of 500 and the closed loop gain of 100. So this is what is the inference that we can draw from the feedback gain stability of a feedback amplifier. Now after having a brief discussion on the feedback amplifiers about the gain stability, now let us move on to the other device which we call it as oscillators. The name itself suggests it is going to oscillate. So the better example that we can consider for an oscillator is a pendulum. Now what is this oscillator is all about? An oscillator is one or it is an electronic circuit which is going to convert the DC energy into an AC energy of desired frequency. So that's such a circuit we call it as oscillator. So whichever the circuit that is going to convert the DC energy into AC energy of desired AC energy of desired frequency, then such a circuit we call it as an oscillator. So an oscillator is and even this oscillator is going to produce a repetitive waveform at the output without the application of external input signal. So whenever we apply the input, this is going to produce a repetitive waveform at the output without the application of external input signal. Before going into the before going into the different types of oscillation, we have let us discuss the classification of oscillators. Oscillators can be classified based on various criteria. The first criteria upon which the oscillator is classified is based on the operating principle. So based on the operating principle, oscillators can be classified as feedback oscillators, negative resistance effect oscillators, and next the other category is based on the type of output waveform. So whether it could be a sinusoidal oscillator or harmonic, we also call it as harmonic oscillators, or the next in the non-sinusoidal oscillators or relaxation oscillators. And the next category that we are going to see is based on the feedback circuit employed. So that could be an RC oscillator or LC oscillator. And the next categorization is based on the frequency of the generated signal. That is, it could be an audio frequency oscillator or a radio frequency oscillator, or very high frequency oscillators, ultra high frequency oscillators, and microwave oscillators. So this is how the classification of oscillators are going to be done. So based on the various parameters, we can classify the oscillators. So first is based on the based on the operating principle, based on the output waveform, based on the feedback circuit that we are going to employ, based on the frequency of the generated signal. So these are the some of the factors upon which the oscillators are classified. Now we know our oscillator is a circuit that is going to produce a repetitive waveform at the output without the application of input, external input signal, right? So now in order to make a device to work as an oscillator, it should satisfy some criteria, and that criteria we call it as Burghausen criteria for oscillation. Oscillation is nothing but it is the movement of the pendulum. The better example I can say is movement of the pendulum is nothing but an example of your oscillation. So what is the condition? The Burghausen criteria is a condition. Now what does this state? So let us consider a block diagram over here. So when we look into the block diagram of this, I can say the negative feedback amplifier in the block diagram is shown with any input, right? So the negative feedback amplifier is shown with any input, then only the oscillation is going to get produced. We shall be that's whether it could be a sinusoidal quantities, voltage, currents would be treated as phasors and gains complex numbers for the feedback amplifier. So this is what is the circuit for the condition of oscillation. Now let us look into that. One technique for producing, one technique for producing sinusoidal oscillation is to use a positive feedback. That is, whenever if we want to produce a sinusoidal oscillation, we are going to use a positive feedback. Positive feedback, we already know, we have already discussed about the feedbacks in the previous videos, but even then positive feedback is a technique wherein a portion of the output of an amplifier is fed back to the input with in phase. So let us assume an amplifier with an input signal V in, which is shown here, and an output voltage V naught, and an output voltage V naught, and the output V naught is the 180 degree out of phase with V in, because since it is a negative feedback, Burghausen criteria, the output is 180 degree, is going to have 180 degree phase shift. If this is so, then I can say, or we can say, our feedback voltage Vf is given by the feedback voltage Vf can be connected directly to the input. So this is what is our VF, wherein which this is connected directly to the input of the amplifier by removing input signal V in. By removing the input signal V in, the amplifier will continue to generate the output signal V naught. Now the amplifier has an input, but the input is derived from the amplifier's own output through the feedback network. Correct? The output is produced through the feedback network. The output essentially feeds on itself and it's continuously regenerated. This is the process. This process is known as feedback, positive feedback. Now, the overall voltage amplification from V in, the overall voltage amplification from V in to VF is 1. That is, we have the phase shift. Whatever the output is producing, this is going to have this is going to produce 180-degree phase shift. And after passing that signal through the feedback network, again 180-degree phase shift is expected at the VF output voltage. Once there is a 180 plus 180, this is equal to 360 degrees. So we can say the overall voltage amplification from V in to VF is equal to 1 and the total phase shift is 360 degree, or even we call it as 0 degree. The product of amplifier gain A and attenuation beta of feedback network is referred to as loop gain. Okay, so we call that as a loop gain. So amplifier gain V naught by V in equal to AF, A by 1 plus beta A, if beta is adjusted such that minus 180 degree or slightly more than unity, the circuit becomes the circuit becomes self oscillatory with no input V naught, with no input equal to no input V in. The condition beta A equal to minus 1 is known as Birkhausen condition for oscillation. So the Birkhausen condition for oscillation. Now let us consider the amplifier with no input, which is as shown in the here. So let us consider an oscillator with no input, that is an input will not be connected at the an input will not be connected to the amplifier. So once we do, consider that and we know there is a phase shift of minus 180 degree. The polarity of VF reverses and the feedback becomes positive. As such, as the switch is closed, a same voltage will begin to build up. The oscillation increases in amplitude. Till the steady state or the steady conditions are reached with non-sinusoidal oscillations due to saturation. So when we look at the plot of a graph here, we can say the sinusoidal waveform is going to increase as and when it is going to be a repetitive one. We say it as a repetitive one, but the amplitude is going to increase till the steady conditions are reached with non-sinusoidal oscillations due to saturation or shown here, right? So whatever the waveform that we are getting, that is nothing but a non-sinusoidal waveform due to saturation, and whatever the non-sinusoidal oscillations that is shown here, because beta A is not exactly 1. Initial noise voltage, so this is what is our initial noise voltage, and steady state envelope limited by current saturation. Steady state envelope limited by current or circuit saturation. So once we have done with this, now let us have a look at how the initial noise voltage is going to get produced. If the Birkhausen criteria states that The Burghausen criteria states that we know the angle, that is the loop gain A beta. The loop gain A beta is equal to, the loop gain A beta is equal to, the loop gain A beta is equal to 1, or it is going to have an angle of 360 degree. The Burghausen criteria for oscillation states that for sustained oscillation, the loop gain A beta must be equal to 1, the loop gain A beta must be equal to 1, and the phase shift around the loop must be 0 degree or 360 degree. So instead of oscillations or self-starting and begin as soon as DC power is applied, it is possible to produce a thermally it is possible to thermally produce noise in the resistors and other components. This noise is made up of all frequency components, but one frequency component F naught of the noise satisfies Burghausen criteria and the circuit oscillates with that particular frequency. This initial feedback voltage is applied and continually reinforced, which is going to result in building up the frequency output voltage, which is shown here. Now, the magnitude of the frequency component F naught, the magnitude of the frequency component F naught, which satisfies the Burghausen criteria, is this is what is the satisfies the criteria. This is what is the waveform that we are going to expect. So, the amplitude of frequency component F naught is much larger than all the rest, and amplitude is limited by the circuit's own non-linearities. Therefore to start the oscillation, loop gain A beta must be slightly greater than 1, and to sustain it, loop gain must be equal to 1. So for the sustaining of the loop gain, we see to that the loop gain is maintained as equal to 1, and if if the oscillator has to start the oscillation, then we see to that the loop gain A beta must be slightly greater than 1, and to sustain it, slightly greater than 1. So thus the practical oscillators can be produced when an amplifier consisting an active device, a frequency selective feedback network to determine the frequency of oscillations. So if a device is going to act as an oscillator, then it is mandatory to satisfy the Burghausen criteria. So this is what is the references that we went through for the preparation of this video. Hope this video is useful to you, and it it is a beneficiary. Thank you for watching.